Okay, so we just got done kind of going over how you're supposed to finish your lab write-up, and we got the numbers there. I just turned the camera on. And now we're going back to chapter 11. All right. Now, this is on the modern atomic theory. And, yeah, in the first semester we had protons and neutrons and electrons and just something like that. But we definitely get much more into it now. And even though it's called a modern theory, it was mainly developed in the early 1900s. And what I'd like you to do is make a list. There's about 6 scientists in this chapter. So I would like you to, and this won't be due till Thursday, but I'd like you to make a list of the scientists in this chapter and maybe 1 or 2 sentences and what they did. What did they do? And that I'll actually put the scientists on the quiz, and you can do some matching and stuff like that. So let's say on Thursday, I expect you, I think there are 6 scientists in here, and write down the name of the scientist and what they did. So if I can give you the lab grade, I can give you a grade on this. We'll probably do a quiz. That's 3 nice grades here before before next week. All right, so let's go back to this. The study of the modern idea of the atom has to come with light. So I said we're going to spend a little bit of time with the physics of light. And I got the slinky out, and we talked about what do you call the distance between the crest? The crest is the top, right? That's why the toothpaste crest. Why do you want to call it crest? I don't know. Because crest means at the top. They thought that was a good name. We're the best. We're the best. There are lots of names that mean the top. Summit, you ever heard of that? The summit, like Summit Church, at the top. Apex, what's apex mean? At the top. We have a lot of words that mean at the top. Anyway, so the top of one wave to the top of the next wave is called a wavelength. So you can have some really long wavelengths, you can have some short wavelengths, and we went into, when we got to here, this is where it got a little more serious and a little more scientific in a way. God made these type of waves that are called electromagnetic radiation. Now that used to scare me when I heard the word electromagnetic radiation, until I told myself, just replace it with the word light. Electromagnetic radiation is light. Oh, you're going to talk about light? Yeah, that's what I said. Light comes in different wavelengths. Look up here above. See over there on the right-hand side? Radio waves. A wavelength 10,000 meters 6 long. That is a really long wavelength, isn't it? But you know what? It travels at the speed of light. All these are forms of light. Let's come on down. Microwaves. Microwaves are kind of small compared to radio waves, but they're even bigger than infrared. They're even bigger than this. If this is called the EM spectrum, the electromagnetic spectrum, all forms of light, what spectrum is this? Julie, what do you think? What do you call the spectrum of light that you can actually see? The visible spectrum. See, to me, these things might be hitting my eyes right now. There could be radio waves hitting my eyes, but my brain, I don't get it. I don't see it. The only wavelengths that I actually perceive are between 700 nanometers and 400 nanometers. This real little thin paste. God said, I only want you to be able to perceive a small little band of light. And everything I look in the room, look around the room right now, everything that your eye sees, your brain interprets, that's between 400 and 700 nanometers. That's the wavelength of light. And that's called the visible light spectrum. Some people call it the rainbow, isn't it? The rainbow is the visible spectrum. And this is where they get that Roy G. Biv, R-O-Y-G-B-I-V. Red, orange, yellow, blue, green, indigo, violet. And that's Roy G. Biv right there. Now, if we go beyond that, if we go to smaller wavelengths in ultraviolet, I can't see it. I actually have a flashlight here that produces ultraviolet rays. Here it is. And let me see if I can find the thing here. Okay. Can you see those right there? Can you see those little beads? They look kind of like white, don't they? Let me get them out. All right, I'll tell you what, let me do a background. Do you see those beads? All right, can you see them if I tilt them a little bit? Pretty bright, isn't it? How about that? Can you see them now? Better? See the little beads? What do you think would happen if I sit here? They just stay like that, just plastic beads, aren't they? What happens if I shine it ultraviolet? This is an ultraviolet flashlight. What are they doing? Watch, I'll take it away. You see what's happening?
It's too bright.
Too bright. All right, I'll tell you what, let me put a white background on. So what's happening to them? I don't know who actually developed this, but the company developed a chemical in there that when you expose it to ultraviolet light, it'll actually change that color there. And some people even sell them as choker necklaces, things like that. And when you go out in the sun, they turn purple and pink. And you get out of the sun, they turn back to their regular kind of clear color like that. So even though you saw a purpleness here, you might say, I can see ultraviolet. Not really. Sometimes ultraviolet will interact with this glass and you'll see kind of a purple color, but you really don't see it. But I know it's there because it's doing that thing to my beads here. Here we go. Okay. So now to go back and there we go. So we go smaller wavelengths in visible light. We get ultraviolet, and let's get smaller than that. What's smaller than ultraviolet? X-rays. Now, X-rays, the wavelengths are really small. You say, well, how small? Well, imagine we had an atom right here and an atom right there. Atoms are small, aren't they? When you get to X-rays, the wavelength is so small it can do this. The light can go in between atoms. And that's why X-rays do what they can. They can actually pass through your body. Now, something that can pass through your body even better are called gamma rays. Now, gamma rays are the smallest wavelengths that we think exist. They pass through my body, but they also, X-rays and gamma rays, deliver energy to the cells and actually can kill a lot of cells. So if I'm exposed to X-rays or gamma rays for a long time, it'll kill a lot of cells. If you kill too many cells, my organs will die. My kidney might fail, or my liver. And if that dies, I will die. And so that's why you don't want to be exposed to X-rays very long or gamma rays very long. The longer you're exposed, the more likely you'll get hurt. All right, are you okay with this so far? A little bit of physics here. All right, have we talked about this at all, this little equation? Do you remember talking about this? Which one of these types of light do you think is the fastest? Is it gamma rays, visible light, radio waves? Which one do you think is fastest? Which one? Gamma? Anybody else have a guess? What do you think, Kyle? What do you think? Gamma? What do you think? That's a little peer pressure there. Does everybody think it's gamma? Well, I'll give you a clue. Okay, what do you think, Aurora? So I'll be the rebel. Okay.
What are the types?
The question is, which form of light travels fastest? Radio waves, microwaves, visible light, gamma rays? Which one is the fastest light?
I think it's gamma rays.
Okay, so now 4 out of 4. Anybody else not think it's gamma rays? Okay, I'll give you a clue. Ready? See this stuff here? You know how fast it travels? At the speed of light. You know how fast this travels? At the speed of light. How fast this travel? At the speed of light. Everything on that page is made of light. All of it travels the same speed. Now, I'm not here to be your physics teacher, but I just want to show quickly. 186,000 miles, not per hour, per second. So the speed of light is unbelievably fast. They have a special mirror on the moon, and they actually fire laser beams at the moon. it hits the mirror and comes right back at them. They have this very expensive atomic clock that goes down to millionths of a second. And they can actually tell you with this much error, within 10 centimeters, they can tell you how far it is from that laboratory to the moon. Now, how long does it take for that laser beam to go to the moon and come back? That's right. Only about 3 seconds. We talked about this before, didn't it? Because you knew how long the sun took, didn't you? At a little over 8 minutes. Very, very good. So it all travels at the same speed. So guess what? Little c in physics means the speed of light. The speed of light's the same for all those wavelengths. But it says the speed of light is wavelengths times frequency. Now, you may not think this is important, but I have a demonstration here. If you don't understand what I'm saying right now, then I wasted your time. Whenever you see anything in mathematics, and it says something like this, 10 equals 5 times 2. 10 equals 5 times 2. If it looks like that, in that shape, if the thing over here cannot change, that's called a constant. If this cannot change, then these two things are what they call inversely proportional. You say, what are you talking about? It means if this cannot change, if this goes up, this has to go down. So when I have really, really big wavelengths, if the wavelengths are really, really big, then what's the frequency of that wavelength? How often does it happen? If this is really, really big, then what's the frequency have to be? Really, really small. So even though red light travels at the speed of light, how many waves per second would go by a certain point? Not very many. Let's go over here now. The wavelengths are incredibly small. Incredibly small. So how often, what's the frequency of them? It's incredibly high. Now, one more thing. It just so happens that if you have high frequency, you also have high energy. Remember how I told you that if you had gamma rays or X-rays going through your body, it would hurt you? The little wavelengths have more energy in them, and therefore they could do more damage. So you want to stay away from gamma rays and X-rays if you can help it. Now, the good news, when you go to the doctor, the amount of X-rays you're exposed to is a really, really small amount. It used to be a much larger amount. When I was a kid, you had to go and get an X-ray. They actually put quite a bit of X-rays in your leg, and they had a real piece of film, photographic film, that had to be developed. And nowadays, it's all done with sensors. When the X-rays go through there, like a tenth of a second, the sensors can pick up what the X-ray is. And if you have a little broken bone or something, they can show that on an image. And the good news now, you don't have to carry around that big piece of film that shows your broken leg. Now they put it on a computer, and they said, I'll put that in the whole system. And if you go to that doctor, they can pull up your X-ray. Another doctor can pull it up. And now that's the world you live in right now. All right, did I talk about photons yet? I think I did. Did I talk about photons? Okay, one more time. The smaller the wavelength, the higher the frequency. The higher the frequency, the higher the energy. So a photon of blue light, which is a little bundle of energy, has more energy than a photon of red. Now, I need you to know all that before I do the demonstration, because here's what you're going to see. All right, so I'm going to show you this right here. Let's go to this page right here, page 310. Go to page 310. All right, I don't want to show you the demonstration if I don't think you can understand it. So give me 5 minutes of really, really focused attention here, okay? All right, so now, here's a little diagram. And this diagram is simply says energy. Okay, so now atoms have electrons. And if they're in their normal place, that's called the ground state. Ground state means I'm where I belong. What I'm going to do is I'm going to excite them. I'm going to excite some of those electrons. I'm going to say, I don't want you to stay in that level. I want you to be more excited. I want the electron to be an excited electron. When you took biology in the 9th grade, I don't know if Ms. Founds did this or not. Hey, Kyle, can you stand up, please? Because I don't want you to put your head on the desk. You can stand. I'll help you. You can go get a drink or something. Just go do something. When you did photosynthesis for Ms. Founds, did you guys talk about sunlight hitting chlorophyll? Did you remember them saying something about the electrons in chlorophyll got excited? So what does that mean? It means that they actually jumped to a higher level. Get that? And then they jump back down. And they jump and they go again, they absorb some more like that. See that? And so here's what I need you to know. I'm going to show you a thing you're going to put in your eye, next to your eye, and I'm going to show you a bright light. Now, when I turn the bright light on, I'll turn all their lights off here. When I turn the bright light on, this little spectroscope thing will act like a prism. And it'll take white light and actually split it up into the colors. It'll actually show you that white light's made of all of Roy G. Biv. So you're going to look at it and you'll say, wow, that's a nice rainbow. And you'll see all the colors. And you'll even see a little ruler. There'll be a little ruler in this spectroscope. It'll say 4, 5, 6, 7. And that stands for 400 nanometers. That's violet light. 500 nanometers. 600 nanometer. 700 nanometers. You get that? Anyway, so when I show you bright light, you will see all of the colors of the rainbow. Okay, that's not really what I want to teach. I want to teach you, yes, a white light's made of all those. But then I'm going to take an element, and one of the elements I have is hydrogen. And guess what hydrogen looks like in a glass tube? It looks like nothing. It looks like air. I want to put it in a machine, and I'm going to turn on electricity. Electricity is going to go through that gas, and it's going to excite them. It's going to excite the electrons. And then, so here's my diagram. Ready? Here are the electrons. This is energy. And here are the electrons down here. And said, I'm just minding my own business, being what I'm supposed to be. If it absorbs a full chunk, and they have a fancy name for that. Does anybody know what they call a full chunk of energy? It's this right here. If I give this electron a little bit of energy, it will not get excited. Well, let me give you some more. No, 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 no. You have to give me a full quantum of energy, this much. If you give me this much, I'll get excited and jump to the next level. And that's why they call it the quantum mechanics model. If you give me a full quantum of energy, here's what's going to happen. I'll absorb the energy, and then you won't see anything. But then I'll jump back down to ground state, and I'll give off energy. Now, when I give off energy, if it's in the wavelength of light you can see, you'll see these. So hydrogen, when I excite hydrogen, instead of giving off the entire rainbow, it won't. It'll only give off certain colors. And it took smartest people in the world a long time to figure out. And they use mathematics and everything, trying to figure, what does that mean? What does it mean? Why didn't you give me the whole rainbow? And what they found out was, it's like this. When I jump up to here, you won't see anything because I'm absorbing energy. But when I jump back down, I have to get rid of the energy. Now, look right here. I could have jumped to here. I could have jumped to here. I could have jumped to here. There are many quantum jumps that I can make. But here's what I want you to see. Do you see the arrow? I should give off a color. I give off a color. I give off a color. I give off a color. Which one of those arrows, 1, 2, 3, or 4, which arrow is the biggest amount of energy change? Which one's going to give off the biggest amount of energy? All right, Zach, you know. Which one gives off the biggest arrow? Is it arrow number 1, 2, 3, or 4? Let's take a look. Yes, that's it. Now, let's go back. If it's the biggest amount of energy, what color do you think it is? Which one of these colors of light represents that kind of a jump down? Which one of these represents the highest energy? Is it violet, blue, green, or red? Violet. Just like we did ago, we said gamma rays and X-rays are the most energy. Look on the visible spectrum. Who has the most energy here? Violet, right? Okay, so the biggest amount of energy here, that must be why you gave off violet light. Which one's the smallest? Layla, your turn. Which one of these represents the smallest arrow? Okay, see that? Now, which color do you think was that one? Which color do you think was represented there?
Red.
Yes. Everybody see that? Okay, and then the second smallest would have been probably green, and then the second biggest was probably blue. Does that make sense to you? One more time. If this was in a ground state electron and he absorbed all this energy, and then he came back down where he belonged, he'd have to give off a huge amount of energy to go down to ground state. Which one of these colors represents the highest energy jump? He jumps back down, gives off a huge amount of energy. This one has the most energy. That must be why you saw violet light. Here's a small jump. The smallest jump, smallest energy, will be something like the orange light. This is the second largest, so it won't be violet, but probably the blue. And then this right here is the second biggest, and it's going to be, second smallest, it'll be the green. All right, so let me go ahead and do the demonstration and see if it makes sense to you, okay? Let me turn this off. I'm going to ask you to, if you're sitting right about here, I'm going to ask you, Liam, if you just move this way a little bit, and you can move that way just a little bit. I want you guys to get up out of your chair and come closer. You guys get closer, okay? This is actually, don't use this without me being in here. But I am going to plug it in, and it'd be very dangerous for you to stick your fingers in there once I plug this in. So I'm not going to plug it in yet. All right, so here's what I'm going to do. I'm going to turn the lights off here in just a minute. And let me show you how to use this. You'll do me a favor. Everybody one of those. And see. You'll turn off both light switches, Madison. Okay, now, if you'll let me show you how to use these, then it makes it a lot easier. Make sure everybody gets one. These are called spectroscopes, and what they do is they take the place of a prism. And so it'll break light into its colors. Thank you very much. All right, look right here. First of all, there's a fat end and a skinny end. The skinny end always goes to your eye. That's easy. Now, look on the end here. Look at the fat end. You'll see a big window. Don't touch that with your finger if you can help it. And you'll see a little slit. Looks like somebody cracked it, didn't it? Does everybody see the slit? Okay, now, here's what you do. Hold it sideways like this. I want the slit to be pointing toward a light. And then, I don't look at the slit. I look over here. So right now, there's enough light bouncing off that car over there. I could actually everybody point toward that window and point the slit toward the window, then look to the left. Do you see sort of a faint rainbow?
Yes.
And do you see numbers in there? Do you see a ruler with some numbers like 4, 5, 6, 7? Okay, so the small wavelengths, the 4 should be the violets and blues, right? And the reds should be the 707s. Now, because that's a kind of a weak signal, I'd like to give you a really bright light. So what I'm going to do is I'm going to turn this light bulb on, and if you point to this and you don't see a rainbow, you let me know. If you don't see a rainbow here, there's something wrong. You ready? Plug this in. So everybody know how to use this, right? All right, here we go. This is bright. Now, where's the slit? The slit's supposed to point, but you don't look at the slit, do you? You don't look at the slit, but the slit should be pointing at that light bulb. But you don't look at the slit, but you're pointing toward me. You point your slit this way. There you go. Everybody see a rainbow? Is it pretty bright?
Yeah.
Oh yeah, that's really bright. Now, what's happening is the light bulb in here has a little wire in it. When you run electricity, the wire is giving off every wavelength of light, and that's called a continuous spectrum. A continuous spectrum. You get that? Because you see all of Roy G. Biv. Now let me turn this off, and let me show you why we really got this equipment on. Now, the first tube, I always save the best till last. So the first tube, we have to be sitting kind of close to see it. But let me go ahead and get this out ready. Let's see, helium, argon. Okay. Now, I'm going to show you in here. These cost about almost $40 a piece, so I'll try to be careful of them. what do you think this looks like? What does argon look like? And it looks like nothing. It looks like there's nothing in here. But there really is argon gas in here. And what I'm gonna do is stick it in here. I'm gonna turn the electricity on, and I'm gonna excite the electrons. Now, argon has, if you look on a periodic table, it has every atom has 18 electrons. And they're arranged in a certain configuration. Just mind your own business right now. They're in their ground state. Doing what they're right. Some are here, some are here. And what's going to happen when I excite them, some are going to make a jump from here to here. Whoa, 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 whoa. They're going to jump up and down, up and down, up and down. And what they're going to do is, without the spectroscope, you'll see one color. With the spectroscope, you'll see it's really made of many colors. And this is the weakest one, so you might have to get a little closer. Ready? Argon, excited. Look at it without the spectroscope. You think there's only one color come to your eye? Now use the spectroscope. And you might have to come a little closer. Go ahead, come closer. You see more than one color? So what do you see? Tell me some color you see.
I see violet.
Yes.
I see a dark purple, and green and orange. And then
You wouldn't have thought there was any orange hitting your eye. Is that right? Eye? Anybody see that? Go ahead, try it. Now, back up, Leila, back up just a little bit. Can everybody see? Now, this is the weakest one. You have to be the closest to see this one, and I'll save the best to last. All right, what do you think? Now, what do you think's happening here is, let me explain this to you. Argon is a different element than hydrogen. Argons or electrons are in a different arrangement than hydrogen. So when you excite them, they make different jumps. And what you're looking at is called an emission spectrum. It emits, what are the colors again? Violet? Only one violet or more than one?
dark purple.
Dark purple, how many? How many dark purples?
Just one.
Any other color you said orange? How many oranges? Just one?
And so two.
Two oranges, how many greens?
Two greens.
Okay, any yellows? Any reds?
Yes.
Yes? Okay, so now, what somebody would do is they would write those down, and that little ruler in there would tell you which red. There are many reds. 700, 660, 680 wavelengths. There are many, many reds, many, many greens. All right, so let me take this out. It should be cool by now. Put him back in his case. Now I'll give you the next one. Okay, here we go. Now this is hydrogen. Okay, what does hydrogen gas look like? You're right, it looks like nothing. But hydrogen, every atom of hydrogen only has one electron. If I can excite it, maybe it'll jump to 1 level, 2 levels, 3 levels. See how many colors you can see. This is going to be brighter. Ready? Look without the spectroscope. Wow, that's what excited hydrogen looks like. But what kind of colors are really hitting your eyes? All right, go ahead, let it go. Orange, how many? How many oranges?
6.
6. Any reds?
7.
Any yellows?
No.
Any greens?
5.
Any blues? Okay, you're giving me the actual wavelength, right? All right. So you see any violets? 1. All right. So what I'm trying to tell you is why did this emission spectrum? Why is it different than the one for argon? Because the electrons started in a different place. They jumped different levels. It's a fingerprint. For a long, long time, if they said, "I think I discovered a new element," oh yeah, prove it. And they would have to do something like this and say, did you give the same bright line spectrum called emission spectrum? Did you give me the same bright lines as another element? If you did, you're not a new element. This is like a fingerprint. Now, the next one I'm going to show you is called neon. And by the way, any company, if you go to Las Vegas or anywhere else, you know what neon signs look like?
Right.
They're bright. And the reason they do it is they're all tubes, and a glass maker made a tube, whatever shape you want, like Hot and Now, pizza, see that? They made that shape, filled it with a gas, and closed it up and put wires in. one at one end and one at the other end. And then, when you turn the electricity on, it will start to glow. Now, if you want to make an orange light, you use neon. But what if you want to make purple? You could use argon, couldn't you? So those companies, that'd be a great extra credit thing. Now find a company who makes these. All right, what does neon look like? Nothing. But remember, neon on the periodic table is number 10, so his electrons are in a different position than hydrogen, different position than argon. All right, so watch it without the spectroscope first, and this is going to be the brightest one, okay? Ready? All right, now use your spectroscope. Even though you think, oh, there's only one kind of light hitting my eyes, orange. Are you surprised to know that orange light actually has all those other? Daniel, give me some colors you see.
I see yellow.
How many? How many yellows?
Only see the two.
Okay. Any reds?
I see 3 reds.
Any oranges?
2 oranges.
How about greens?
I only see 1 green.
How about blues?
I don't think.
Okay. How about violet?
Yeah, I don't think about it.
Okay. Now, will you all agree? Will you all agree with me that the emission spectrum, the bright line spectrum you see here, is that the same as any of the other two gases, or is this unique?
Unique.
It is, isn't it? And you can actually do this. You can actually use this to identify elements. I have a couple of students that took one of these at home. They were going to do an extra credit project. And so what you would do is, for example, they might do a regular light bulb and get their colored pencils out and make a little box, say 4, 5, 400, 500, 600, 700, and you actually draw a rainbow at the different wavelengths. That's the first thing he did, is what they call continuous spectrum. Then, some of them are going down to the gym. The gym has really bright lights. Did you know that? You know what's in there? That is not a regular light bulb. What's in there is called a mercury vapor. It's vaporized mercury that's excited, and it gives off a huge amount of light. But if you look at it with a spectroscope, it's not the continuous spectrum. It's not all the colors. It's only certain ones. And then some of you have street lights at your house that are kind of bright. If you look at the street light, you'll see another fingerprint of bright lines. Some neighborhoods have an ordinance that said you can't have those bright lights. You have to have the dingy street lights. Does anybody live in a place where they have kind of dingy, dull street lights? And those are called sodium vapor lights. That means that they have vaporized sodium in there. They're going to give off a different fingerprint. How about your headlights? You ever see cars where it had a regular headlight and then the ones that are super bright? What would be the difference with them with the spectroscope? Do any of you have grow lights, grow plants? You have special lights to grow plants? Okay, they actually make those. And if you had a grow light, you could point it toward a grow light to see what colors are really being emitted from that. I hope I didn't waste your time. Do you have any comments, questions you have about this? The reason this happened, when they started doing this with all the elements they could think of, they started seeing patterns and they said, I think this means something. And they used a lot of mathematics and they figured out this, okay? Look at my hands here. Here's the nucleus, ready? Nucleus is really small. The electrons are not in the nucleus, they're in these locations. And I think your middle school teacher would have said something like this. They would have said shells, electron shells. Do you remember anybody saying that? Did anybody say they were in electron clouds? No? None of this rings a bell? Did they say energy level? Did they use the word energy level? So we have energy level number 1, energy level number 2, energy level number 3, number 4, 5, 6, 7. We think there are up to 7 energy levels that electrons can be at. But you can't find an electron halfway. You aren't going to find them at level 1 and then level 1.5. There's level 1 and there's a big jump to level 2. And that's a quantum jump. Anyway, that's what's going to start the rest of the chapter. The rest of the chapter, we're going to talk about where the electrons are and what does that have to do with the shape of the periodic table. Why is the shape of the periodic table so weird? How many elements are in the top what they call period. Period number 1, how many elements are in there? 2. How many elements are in the second period? 8. Look at the third period. 8. And then it goes 18, 18, 18, 18. You get down to the very, very, very bottom. There's, see where it says serum, praseodymium, and neodymium? See at the very bottom? There are 14 there. Well, what I want to, if I can, if you allow me, I'll try to, on Wednesday and Thursday, I'll try to show you this pattern that exists. Okay? So just let me do that. How about, any questions on this? All right, you did a great job. Okay, put these back in kind of gently. They're pretty nice. If you ever thought about doing something besides, if you want to do a little extra credit project, come and see me and say, I have an idea, here's what I would do. I'll tell you something, my son, he doesn't work with it anymore, but my son used to work for Disney World. And in Disney World, you actually find out all these little things that they do. And because they have a lot of money, they're able to hire people that do things that you don't think about. For example, they have sidewalks that are made a certain color. And they know that when the sunlight hits it, it'll reflect and it gives a better picture. So when people take pictures, the light coming off of their, some of their sidewalks make you look better. They also have things that they do in Disney where it has to do with lighting, and they have experts that actually have figured out what to do. And they get paid a lot of money to figure this out. All you do is go to Disney World and have fun. But what they do is all about image. They have, for example, I don't know if you knew this or not, they don't want a little boy or girl seeing Mickey Mouse right there and then seeing another Mickey Mouse over there. That's confusing. Why would there be 2 Mickey Mouses? It's like seeing 2 Santa Clauses at the same time. They don't do that. They have Mickey Mouse that come out from all of Disney World, did you know, is on a second level? Everywhere you walk is a second level. Underneath there is a whole little city underneath there, and they pop out at different locations. They go up the stairs, all of a sudden Mickey Mouse appears. And they have it timed so that Mickey Mouse, when he leaves down here, and another Mickey Mouse will show up somewhere else, and they're never seen at the same time. And there's a lot of little things they do there. They don't want you to see building going on. If there's some construction going on, they don't want you to see it. They want you to have this experience of being in like a fantasy world. They do another thing with buildings. They have a building, and they want you to appear as if the building's taller than it really is. The artist makes it appear to be taller. It's called perspective artistry. Have you guys done, have you in art, any of you guys in art? Have you had perspective drawings? Well, they'll actually do that because you're looking up, but it's really not as big as you think, but they drew it so it looks like it's taller than it is. All right, let me put this up. All right, hey, I want you to work on your lab report, okay? Work on your lab report, and then just come back to class on Wednesday, and we'll start the other thing. All right, bye.
Do the Thomas.